شرکت کننده های عزیز خوش آمد میگم همون و از کسایی هم که دو روز قبل با ما همراهی کردن تشکر میکنم، هم ارائه دهنده ها و هم شرکت کننده های محترم. امروز انشاءالله ما فکر میکنم که 8 سخنرانی داریم و 2 سخنران اصلی داریم. توی 2 جلسه برنامه ریزی شده. اولین جلسه همون که الان شروع میشه آقای دکتر شیخ شباری رئیس جلسه هستن و سخنران اصلیمون اولین سخنران آقای پروفسور چایچیان هستن. اجازه میخوام که به انگلیسی هم بهشون اعلام بکنیم که جلسه شروع شده. Hi, Professor Chaichian. This is the third and the last day of our conference on physics of particles and fields. We have 2 sessions in this day. In each session, we have 4 speeches. The chairman of this session is Professor Sheikh Shabari. Shahin, if you hear me, please start the chairing of this session.
Okay, thanks. من این قسمت معرفی رو فارسی میگم چون ایشون سخنرانمون خیلی خوب فارسی میفهمن و صحبت میکنن، ولی سمینار رو میخوان به انگلیسی بگن. ما امروز خیلی خوشبختیم که آقای پروفسور چایچیان برامون صحبت میکنن. صحبت ایشون خیلی علاوه 5 دقیقه است و راجع به مدل های دارک ماتر و گاما ری برس صحبت خواهند کرد و من یه معرفی مختصری بکنم ایشون رو. آقای پروفسور چایچیان که در استاد دانشگاه هلسینکی بودن، چند وقت پیش اونجا بازنشسته شدن ولی در واقع به کار ریسرچشون ادامه دادن و خیلی هم تو این کارهای مهم زیادی انجام دادن. از جمله اون کارهایی که من خودم باشون در واقع افتخار همکاری داشتم در حوزه نان کامپتیتیو جیومتری و فیلد تیوری روی نان کامپتیتیو پلین بوده و فکر کنم کارهای ریسرچشون معرف حضور همه باشه. ایشون هم چندین کتاب دارن، کتابای تو سطح مختلف که حتما فکر کنم شنونده ها با این کتاب ها آشنا هستن. خب من از ایشون میخوام که صحبتشون رو شروع بکنن. بفرمایید. متشکرم.
خیلی متشکرم. اولا سلام به همه دوستان که متاسفانه همه رو من ندیدم و به اصطلاح معروف به کسی این سایت چیز نباشه، اتفاق نیفته برای هر کسی، ولی در آینده حتما میبینیم هم دیگر رو. قبل از هر چیزی باید من البته باید اعتراف کنم که شرمنده‌ام که این صحبت رو به انگلیسی میدم و این یاد من میاره که هرمن ویل موقع که در امریکا بود و کتاب معروف خودش رو که اسمش از کلاسیکال گروپ رو نوشت، مقدمش نوشته که سرنوشت روی من یک یوغ سنگین گذاشته که این کتاب رو من به زبونی بنویسم که مادر من در موقع در نزدیک گهواره من لالایی برام نمیخوند و این علتش بود که این داشت می‌نوشت به انگلیسی و زبان مادری این آلمانی بود. ولی علت این که من انتخاب کردم انگلیسی چون راستش رو بگم اینه که اصطلاحات رو من ممکنه قاطی پاتی کنم بعد زیاد معلوم نباشه درباره چی صحبت میکنم باشه. So usually in these conferences not everybody, people start to speak about some problems or some phenomena which have been explained well or they have contributed, and then the audience will say what a genius person is. Now in this talk I have chosen a subject which is a problem, and it is as if some people have explained it, but I would give the critics to them, and also what I have made also, I have not succeeded. So it is a good problem also for studying and investigating further. Now, I want to speak about, can dark matter explain gamma ray burst delay, which is experimentally has been as if observed, without invoking the drastic assumption of Lorentz invariance? Because if you just change Lorentz invariance without general relativity, it is an inconsistency. Now, this has been collaborated with Breivik from Norway, and then a former of my student, or our student in Helsinki, Oksanen. So, experimental observation, that is, Antares experiments during the years 2007 and 2012, they observed some bursts, gamma ray bursts, and then when they took the experimental data, their own, and also from Ice Cube experiments on neutrino, and they analyzed very complicated way, and they came as if there is a delay of gamma ray burst, which are coming through the interstellar space, and they are very energetic. They are starting of the order of 1 TeV to 100 TeV. These are very, very high energetic. So people jumped that, yes, gamma ray burst came later than neutrino because Lorentz invariance is violation. I will tell you, I will come to this later, because this is a very, very interesting job and subject, and there have been so many papers written on these subjects that one has to be a little bit maybe thinking. Now, to this Lorentz invariant violation interpretation of the data will come later in this talk. Now, I thought that maybe this gamma ray burst can be explained through the dispersion of light in interstellar space. After all, light moves from where they have been emitted up to us such a big distance, and then there are all sorts of particles, and then if light disperses over those particles, then of course it delays. This is the standard physics. Of course, will involve a lot of new things inside. But let's see what happens now if we consider different media where the standard models, not standard model, standard physics can explain. Of course, standard model also comes in and so on. Now, so it is dispersion of light. So this medium, when we can consider, because it's very, very rare, they are not very dense, they are considered they are plasma. This is the definition of plasma, because these are very, very high energetical rays, gamma rays, and then the wavelength is by order of magnitude smaller than the distance between of the media particles. So then it is a very classical thing, and dispersion relation, it means the coming K is the wave function or wave vector of the coming photons, let's say waves, and this omega plasma square. So when you add these things, then you get the energy of the outgoing gamma ray burst. So if we use this formula, which is classical, and you can derive it in classical electrodynamics, then we will get for the plasma frequency, is called plasma frequency, which adds to the energy of the incoming K squared, this is incoming ray, and then this is the outgoing ray. So this is photon, and then this is from classical electrodynamics. One can calculate it, and these are in many books. One of them is, for example, Jackson or some others, and then another one is in a book by us. So this can be found very well explained and so on. Now what is N? N is the mean number density of the particles in that plasma. Epsilon is the permittivity in vacuum, and it is very near to, for the plasma, to 1. So this is the formula for the plasma, and it adds to this formula for the formula 1. Now let's see what happens. So as usual, everything one can derive also from quantum field theory. This I learned from a course I took many years ago by Abrikosa, this Nobel Prize, and he stated such a thing, but he never taught us how to get it, how to get all these things from quantum theory. But the opposite is not true, because you can have things from quantum field theory, but not you cannot get from classical electrodynamics. So this is a new way we get for the dispersion of the light on a, let's say, for simplicity, we take electron plasma in the interstellar space. So the diagrams are the two Feynman diagrams. This is S channel, and then this is T channel. Photon comes, electron comes, and gamma goes electron, and these two diagrams. When we add these two diagrams and we take the limits where omega is very big, it means the total energy of the gamma ray is much bigger than the plasma, which happens here. So one gets the limit of the classical one, which was this limit, which is the formula 2. So formula 2 we get also quantum field theory. We'll be using this technique later. So then we have to see what is the gamma ray burst, V, this is the velocity of gamma ray burst, which after dispersion, and then it is, as usual, the derivative of the energy of the d omega over dk, and this is the group velocity for the gamma ray burst which is coming out. So it is equal to, we get c minus omega p squared divided by 2 omega squared is 1. And of course, it is less than c. It means dispersion of light makes the light to delay. So c is 1, let's call omega p square plasma square over 2 omega square in this formula 3 by the letter D. So in order to get a gamma ray burst delay, what the experimentalist says about between several hours and a few days, one needs D to be 10 to power minus 14 or more. Now we will see what happens if we take the plasma to be electron. So electron mass we know, and then let's take the gamma TeV, this best we can get if the energy of the gamma ray is 1, is the biggest delay we will get, right? Because velocity will be much less than c, as if. But we will get for the group velocity of gamma ray burst 10 to power minus 15 multiplied by n. density of the electron. This capital N is the density, average of the density of electrons. And of course, this will give zero effect. You don't have such a delay, not delay at all. So it is out, because if there will be so many plasmas in the electron in the plasma, of course we would see it, and we don't see it. Now let's try other cases, the other plasma. So let's say for something like axions, because from this formula, we see that in the formula appears, this formula 2 appears here, electron mass, right? So if we take an axion, maybe it will help, because axions are now very popular, and it is also at the same time, as if a good candidate for dark matter and so on. So let's take to be a axion plasma. Why not? Because axion has gravitational force, and near the very, very heavy stars, it can be very dense clouds of the axion plasma. So axions has a very small mass. Now we have to see, but axions are not electrically charged, right? They are neutral. So, however, axion has coupling interaction with the photon through the loops, which we will see now. I think. Actually, these axions have been so now popularly used by Wilczek and a lot of people, and these are, it is even in the solid state physics now, it has become a big subject in solid state physics, in the so-called topological insulators, and then there are also CERN, axion, solar telescope, and a lot of activities are going. So the assumption of axion plasma is natural. Let's now see what happens if we consider plasma axion. Now, there are a lot of evaluation, but the best evaluation, one of the very recent work by Pierre Sikivi, which was done a lot of work on axions, just like Wilczek. And then when you calculate, to see what is the coupling of the axion, which is an axial scalar. It means it has spin 0, and then it is axial. It is like pi meson, so parity negative. So so the Lagrangian in electrodynamics, it is not parity violating, so it is F mu nu. F mu nu is the tensor for electromagnetic field, and F tilde is its dual. It means the same thing multiplied by epsilon. You know that when you multiply something by epsilon, that becomes pseudo in parity, right? So this is a tensor, this is pseudo tensor, this is axial, so it is parity is conserving. And this evaluation or for G has been done by many people, but one of the evaluation is I have written here, and I give all the list of references where it can be consulted, the exact thing. So G becomes very small. Now, what we need, now we know G, we have such a Lagrangian. This is very complicated Lagrangian. When we write it, we want to have classical derivation. So now you have to see that what is the dispersion relation of light in a plasma which has axionic. And this formula, which is omega squared, is k squared c squared omega plasma squared. It is universal, always for any media, but we have to find omega plasma square. Now, there has not been any derivation of it in classical electrodynamics. We tried to do with all our expertise, we couldn't get. So we said, I remember that what Abrikosov said, that everything you can give quantum field theory. So we did it from quantum field theory. So now, what is in quantum field theory? Photon is coming on axion and propagates through virtual photon, and then this photon and this one. And then this is the from omega T, and there is another also T channel. These two diagrams, U channel and T channel are the same, identical. So the formula we obtained, it is omega plasma square. It is 3/2n number of axions in the plasma, the density of the axion in plasma, and G square M axion. Now, knowing all these values for the M axion and this evaluation, of course, theoretical, which look very reasonable, and also G, then we calculate and we see what N axions we need. Now, omega plasma is 3/2. This is the exact coefficient. The number of H G square M axion. And by the way, this reminds, it is very much analogous to the what we got in, we know for electron plasma. You see, this G has dimension of 1/mass. So its square is 1/mass square, and then it multiplies by M. You see, as if effectively mass of axion has gone down here, just like electron. It is very interesting. So these are new things, but of course they are technical. And so on. Now, let's see what do we get if we put all these numbers for the dispersion of light. So dispersion of light is the same formula, and then for get D is equals 3/4, and this and axion omega square. Omega is the incoming photon energy. So let's take it gamma ray burst. So we take the best 1 TeV, and with all this evaluation, what we get, D is 10. D is 6 multiplied by 10 to power minus 88 multiplied by N axion multiplied by meter square. So we need a big, because we saw that the delay of a few hours, if the experimentalists are correct, and most probably are not correct, because this they are not, I will explain. So D has to be of the order of 10 to power minus 14. So we need a very big density of axions, which is out, experimental given. So the delay of the gamma ray burst, now how is this delay when we are speaking, because experimental said that this delay of the gamma ray burst is compared with the neutrino burst, which they connected. So if we accept this is now another assumption, then tau, we can never get such a delay with this N axion. Now because this axion we have taken also the best, because we assume to see what delay we get maximum when we take the best values, 1 TeV for the energy of the gamma rays, and then the D, the distance the gamma ray burst traveled through all the universe as a diameter of universe, which is 10 to power 26 or 10 to power 27 meter. So this, in order to have a tau, what the experimentalist says, it is a, let's take it, what value the experimental gives, something a few hours. So we took 3 hours something. So D is the we take it deliberately as the diameter of observable universe, which is about 8.8 multiplied by 10 to power 26 meters. So what we need in order to have such a delay, N axion has to be 10 to power 73, extremely density, and it is out by experimental data. How it is out by experimental data? The estimate is the following. Let's look at the galactic halo, which we know what it is, and this is the nearest galactic to us. And we know it's because of the dark matter density, total density. We know we know the diameter of this galactic halo is 10 to power 20 meter. So you see, very far from us, because the diameter of the whole universe is 10 to power 6. You see. So if we take this galactic radius and then we calculate its volume and we know the density, then we find the density of the mass density of these axions, which are, if we assume that the dark matter observed in this galactic is this is the density, and then we get that the number of the galactic halo, which can explain the number of axions, density of axions per meter 3 to power 3 is 10 to power 20, and we need 10 to power tremendously. We need it. Let's look what we needed. 10 in 83, we need 10 to power 53, and then it is out. Now it is maximum. The axion can be, the density of axion is 10 to power 20. So it is also out. So we are already a little bit troubled. What to do? Yes, you see, dispersion does not explain this delay. Most probably this delay is not correct, because they assume that this is neutrinos are connected, they have been emitted at the same time. So an axion is of course, there are details, but they have taken the biggest you can see, because we allowed the the gamma ray bursts go through the whole universe, while galactic size is much smaller. But this is assuming that there are many galaxies further and they have the same density. Of course, one doesn't know, but this is it. So, by the way, this galactic has become a lot of also popularity, and there are work by Wilczek and so on. And then they call it when there is a action like plasma, then there is also a Casimir effect it has. And also in the space-time, it has birefringence because it's axial. See, it's called axial medium in general. So these are, I'm not interested, but I wanted just to say. Now, of course, we know that CMB, cosmic microwave background, and there are also a lot of photons around in the interstellar, also next to us. So let's see what is light dispersion makes on light, like cosmic microwave background. Again, so we have to find omega plasma for this case. So it's not given to in the, of course, literature nowhere. So we go again to quantum field theory. Quantum field theory, we have to calculate these diagrams, and after that, according to our calculation, where we used Bohr and Ayer's formula for the wave dispersion and wave motion. So having used this, we need to have to calculate this diagram, and from them to get omega plasma square. They are not just a diagram. But this diagram have been, these are very important. You see, by the way, here there is no classical derivation from electrodynamics because there is no loop there. You see, here, light and light go only through. This is only quantum field theory. So we have a point that quantum field theory, we have to start from there to derive. So this has been Euler. This is not Leonhard Euler. This is Hans Euler, which was a student of Heisenberg. So he calculated in some limit in 1936, and Heisenberg and him, they calculated in other loop in their nonlinear quantum electrodynamics, you see, it's called Euler-Heisenberg. And then Akierzer in 1937, that many people, they check their formulation, which are, and then Bredsky, Lifshitz, and Pitaevsky, these are also students of Landau, Pitaevsky, and Brzezinski. They calculated, in their book, Classical 1982 English version, they give some expression again, but not what we need in those limits. So we calculated. This is, of course, straightforward, but it's very interesting. So we calculated and we found the derivation of the omega plasma. Omega plasma is now a constant. This constant, it is of the order of 1 or 10. It's not important for our estimates, because why this constant appears? Because here in the loop can be electron, not can be, one has to take electron, quarks, all the quarks, muon, all the elementary particles which come here of a standard model, we put here. So then we get a formula that plasma frequency square is a constant of the order of 10. The density of gamma, the density of photons in the plasma, in the space, and the charge of the electron to power 4 divided by omega. Omega is the energy of the gamma ray burst. Now let's see how we can get something. Now from the, if we take CMB data from Planck data, for example, the last values, for the number density of the photons in the space we can see nearby, it is 10 to power 8. So one cannot explain again. So whatever it is, it would be reasonable with talk. Now we will come to the alternative. Of course, this alternative is not good, but here we have possibility to see many other things. So let's see what now Lorentz invariant violation people did.
Masoud, you have 10 minutes.
10 minutes?
Yes.
Okay. You're okay, I will hurry up. So first time, by the way, Coleman and Glashow wrote a classical paper that yes, Lorentz invariance can be violated, but it has to go to several of his subgroups, which is what is usually the case. You cannot just say it is violated, but no group, because physics, everything is on the symmetry. As Dirac says once in his talk, that a correct physical theory has to have mathematical beauty. And mathematical beauty is only in the symmetries or some principles. So Coleman, and after that, many people, they started to work on this one. Now, this Lorentz invariant people who have worked the Lorentz interpretation through the violation, they usually change just the dispersion relation, and where it comes is not known. So dispersion, it means the relation between energy and P and the momentum and the mass. But does dispersion relation always change when Lorentz invariance is violated? No, the answer is not that, and is not necessary. So example is non-commutative quantum field theory. Non-commutative field theory is a theory where it has quantum mechanics effects like dispersion, uncertainty relation, that at very, very high energies you cannot have this measure the very small, very short distances. And this, there were very many attempts and so on, but the seminal work was done in 1998 by Ardalan, Arfai, and Sheikh Jabbari. And later on, after 1 year, Zyberg and Witten were inspired by this work, and then they look also through string theory, and then they came to a conclusion, yes, in string theory also with a certain background, there is non-commutative. It means space points, they do not commute. They are like operators, and there is an uncertainty on distances. This is very physical theory, and here Lorentz invariance is violated. However, dispersion relation is not violated. This was shown a work in 2004, and this is a counterexample that not that just changing the dispersion relation and then you will get the Lorentz invariant violation. Now, there were two groups. The first group, which started with many works by this thing, was just they were coming gamma ray burst, but they did not compare it with the neutrinos burst, because at that time there were no data. This for the delay. So they just looked at gamma ray burst, and then they said, yes, this will show because Coleman and Glashow, and they said that it has to be violated. They considered it, and they changed the dispersion relation, and changed, for example, dispersion relation, and a theory which is by Lukerski et al. Was proposed in that year, and it was called Kama Poincaré. But Kama Poincaré, in fact, is not a flat Minkowski space. There is a 5-dimensional sphere, and after that, the radius is a parameter of this sphere. And then when you take the parameter, this radius to infinity, it becomes flat. So it is actually not Minkowski space, it's not flat space. But anyhow, they took the dispersion relation from there. And then when after 2007, when Antares published the work, immediately to, by the way, all these people are my friends, but I criticize them. So Jacob and Piran is a very, very famous astrophysicist, and they immediately, this was the gamma ray burst compared with neutrino, was observed in 2007 and on, and immediately Jacob and Piran, they wrote a paper that yes, this is a Lorentz invariant violation. How? Because if you do special relativity dispersion relation, you change it by such a formula, you see. It is the formula for the photon is massless. This is the usual Einstein Lorentz invariant dispersion relation, but there is a P4 to power C, epsilon is parameter, you see. So the more you pump to a photon momentum, energy becomes less. In other words, you increase energy of E, momentum becomes less in a very high energy. It is a little bit strange, but it is a deformism, mathematical thing and so on. So, or in general, they fit it with all sorts of powers of this. This is the dispersion relation, Lorentz invariant violation. When you took the groove velocity from this formula at the very high energy, this term dominates, you have groove velocity for the photon is C multiplied by psi energy of the photon over by energy over energy which is called quantum gravity, because quantum gravity, of course, after corrections can give the dispersion relation different, but then it's not Minkowski space because it's a gravity. So this is a little bit, it's not a little bit, fully inconsistent. So this energy of quantum gravity that enters the Lorentz violation is taken 10 to the power 19 GeV of the order of Planck scale. Now, so now what we have to do, we are in two different interpretation of gamma ray bursts, if at all gamma ray bursts exist. So light dispersion in cosmic plasma is this formula or the Lorentz invariant violation, but they are different. They predict that if you increase the energy of the photon coming, light dispersion. So velocity becomes very near to C, this formula, light dispersion in cosmic plasma. So the more energy, the more the velocity of the photon in the plasma stays near to C. And when energy decreases, the opposite. The velocity of the photons becomes less than C. Although it does not explain that amount of 3 hours, but this is the frequency dependent of the delay. But the Lorentz invariance violation is the opposite. If the more energy, the less the groove velocity comes. So what will happen here? We have failed, as if with those delay, for the delay to explain dispersion by dispersion relations, and Lorentz invariance violation also cannot explain, by the way, by this thing, because psi must be about 1 in this Lorentz invariance violation of the delay. It cannot be explaining delay. The only thing it can say that the frequency of the different photons compared with the dispersion relation are the opposite. So experiment can only distinguish between two explanations, although numerically we cannot fit. So there are future experiments planned, and they will decide on this very precise, and they will see how they look just at gamma ray bursts and forget about delay compared with neutrino, and then to decide between these two things. So now let's see what is about neutrino. If we take neutrino, we already assume
you have few more minutes, please. If you can
4 minutes.
Hurry up.
4 minutes.
Yes, maybe.
Of course. Neutrino bursts, we took until now that neutrino bursts are no dispersion, and it is true, because dispersion relation of neutrino is interaction with the plasma is very small. So dispersion we can easily forget. However, neutrino has mass. So if we take neutrino of mass and oscillation of the neutrino from going through the all interspace, oscillate, and then we take the average mass, because many times they oscillate. So neutrino also is very, you see, it has to be 10 to power minus 14, but it's 10 to power 26. It is practically like energy C. So this assumption we took all over, it was correct. Actually, I have spoken with experimentalists who have been involved in Antares and also ICE Cube. They told me that actually it's not known whether these neutrino bursts are coming from where. So one cannot say that there is delay or even the opposite, because we don't know that they are coming from, first of all, interstellar source, and whether they have been from the source, the same source as the photons, and at the same time they have been emitted and so on. They don't know. So probably they are absolutely independent. So what is we can come, I think, this about Abraham Minkowski, there is a controversy, but I will not speak this. There is two transparencies which are not really related with that and so on. Now, conclusion. Invoking Lorentz invariant is not consistent. Modified dispersion relation should be universal. If you do modify relation for the photon, you have to use the same neutrino dispersion relation for neutrino, and not that particle dependent. So this you cannot do. In that case, you don't get any delay of neutrino and gamma ray burst. And in addition, breaking special relativity implies breaking of general relativity, because this is special relativity. It means for the uniform transformation of the speed, but generally it means the diffeomorphism invariance. It means for arbitrary transformation from another system and the other system, they have to be equivalent. So this, if you change this, you have to change also this. You have to change also general relativity. So then you have to have a new theory, which does not exist now, compatible. So while general relativity laws all have been used for all these cases, dispersion of light in a variety cosmic plasma did not explain the gamma ray delay. I assume that this gamma ray delay is not experimentally established, and it's not even, maybe even there is no delay, we don't know how I was stored. But if, and besides all these averages we took in dispersion relation, they were all averages of the, as if the space-time is very uniform. Here it is, and the whole universe, while it can be not like this. For example, axion can be very, very dense and very, very far near stars, because it's also gravitational force become more, they can be very dense, but we took the averages. So these are not very good, but this does not explain. Then if we would manage these failures, and if we can explain all these things, it can be only making through the more precise looking at microstructure of the universe, because we have to know in which regions are more dense, for example, dark matters, or more gamma CMB sort of photons. But what is all clear, that only future planned experiments which will see spectrum resolution of light, namely a gamma ray burst comes, then they will see which one in the blue right, or the blue towards blue, or red light towards red, they come earlier or faster. If blue comes faster, so dispersion relation has to be explained, and one has to work on that side. If the blue comes later, this is Lorentz invariant violation, although there is no theory, but okay. So then you have to work in that direction. Thank you, I finished. I think it is more or less in time, yes.
Thank you very much for the nice presentation. If there are no questions, please ask them. Actually, in the chat section here, there have been 2 questions. Maybe if they're present, they can ask the questions themselves. Any questions? I think you can turn on your microphone and ask the question if you want. So
you can raise your hand.
Okay, so but
دستتون رو میتونید بالا ببرید. من میکروفونتون رو یا دکتر میکروفونتون رو باز میکنم.
So anybody who has question, please. Okay. Let's see. There was one question. I couldn't open the microphone, so let me.
Maybe I can read it. Read the question. Yes.
بله بفرمایید.
سلام، خیلی ممنون از سخنرانی خیلی خوبتون. من سوالم که تو چت نوشتم این بودش که
would you do it in English, please?
Oh, sure. So the question, thanks for the very wonderful talk. My question is that the parameters of axions that you used were those of QCD axions, the mass and the decay constant. So what would happen if you use the parameters of the ultralight axions, for example, with masses as low as 10 to the minus 22 electron volts. I don't know the decay constants, but
yes.
would that change anything?
This is very relevant question. Actually, it is true. There are many versions of axion. We took that extreme QCD actions because this is the most natural. Because axion, after all, they came from the strong CP violation, and strong QCD axion is actually solves a few questions. One of them was the big CP violation, which we have observed, and it cannot be from answered by standard model. So this is at the same time it solves a lot, and then it can be dark matter responsible. Then we can also, what you ask about to the other case where ultra, not QCD, and that we also drop the numbers, and again it doesn't
Oh, okay.
solve. It doesn't have, you see, because mass becomes smaller, but also you need the extreme density, but still the density needed what 10 to the power 57 per cubic meter. This is huge, and it is out.
Yeah, they might be small, but I'm not an expert, but I think the decay constant is an independent Fourier parameter. Can you tune that?
Yes. Yeah, in this formula, which I could show to you in one of these transparencies, which I escaped because the time was not good. I mean, not enough. Sorry. So you mean this one? Yes. Yes. Still more. Yeah. I have to go back. Yeah, right. You see, in this formula, if we go the G, yeah, still further. Yeah, you see, this is axion. It is true that this G is the coupling constant. Now G is a G gamma. It is the one constant, which you can calculate in different series. It doesn't matter. It becomes the numbers over some numbers. You know that the masses of this thing, they are all of the order of 1. Crucial one, as you notice, this is alpha over P, you put here, and then FA. FA is decay constant of axion, and it is taken different values. It is very big, 10 of the order of 10 to the power 15, even some more. This is FA is very similar to why it's called decay constant, because it is like pi meson decay, which is called the decay. That's why the same letter is decay constant. So this we have taken a typical big value of the 10 to the power 15 order, right? But all these numbers of order, if you change it of the order of 3, 4, 5, it doesn't change, because it is the 10 to the power 53, it has to be density, and there is out of question, because it n to the power 10, 53, then you have to have huge amount of dark matter, for example, in galactic halo, which has not been observed. Yeah. So this was a relevant question, but we have look at this number and so numerology and different. Yes.
Thank you so much.
I think we are sort of running over time. If there are no urgent questions, we can thank the speaker again for the nice seminar and move on to the next session.